Court. All right. So close that. So in the video that I got you guys to watch, thanks for doing that, by the way. And sorry, um, but hopefully the day after Halloween it was kind of a welcome break. So we did talk about, or we introduced classification. Oh, and I guess what I wanted to say was, and let me see here. It's tough because it's one of those scenarios where I can't see if there's a chat. So if you have something to say, you better unmute yourself and say it. For the lab tomorrow, it'll just be instructions just like before. So no attendance needed, right? Just work through the instructions, or you might still be working on the chapter 4 one, that's fine. Just work through the instructions. In general, the rule is you have to stay for 15 minutes, but if no one's there after 15 minutes, then I leave. There is a work union meeting tomorrow night, so if no one's there, I will leave. So in terms of classification, which that video introduced last day, it feels weird because I feel like I didn't say it, although, I mean, past me did. But classification is when we're predicting categorical variables, specifically binary variables, right? So we're predicting categorical, and maybe I'll say predicting 4 categorical variables, specifically binary variables, right? 0, 1. And we talked about how we can create binary variables. Okay, so we did introduce some other classification or some common classification models. And then we finished with logistic regression, which is probably the most common. Okay, so we introduced some common classification models. Naive Bayes, for example. Which finds the probability of an outcome given some predictor variables, and those specific predictor variables. We also talked about linear discriminant analysis, which is called LDA, which leverages the covariance matrix, but also it was pretty revolutionary at the time. So when Fisher introduced it, it was revolutionary, but now we're gravitating more towards logistic regression because we have all this computing power, right? So logistic regression is kind of the standard now. One thing to keep in mind about logistic regression is that it predicts the log odds or the logit. predicts the log odds, or could call it the logit if we wanted to. Okay. So it gives us a probability of being case one. Okay, but before I write that down, I'm going to say that the log of the odds that y equals 1, so that's the log odds, is what we're going to be modeling with a multiple linear regression equation, right? Which takes the form beta naught plus beta 1 x1 plus beta 2 x2 all the way up to beta q xq is what I have here. Okay. Which is just a multiple linear regression. And so that's why we consider the log odds, is because instead of being on a 0-1 scale, which is what y is on, right? Then we can expand it and go from negative infinity to positive infinity. And then now all of a sudden we're talking about in terms of a multiple, oh, can't write at all today. Multiple linear regression. This, however, gives us y hat, right, which is the, right, so that's just shorthand. So the predicted value of y is this multiple linear regression, but then we use that to find the predicted probability of being case one, p hat, is 1 over 1 plus e to the negative y hat, right? And so this y hat is what we use here, which is really a placeholder for this entire thing. So one thing to remember is that each of these models return the probability of being case one. Return the probability of being case one. So y equals 1. Using those probabilities, right, that's where we can decide, okay, if the probability of being case one is high, then I'm going to say that I predict that it is case one, right, or case 0. So then we use these probabilities to predict whether each case is 0 or 1. Using a cutoff value, right? Anything with a probability greater than 0.5 is kind of a common cutoff, right? Is going to be considered 1, right? Anything greater than 0.8, then I want to be really sure that the probability of it being case 1 is really high, right? So you can change that cutoff value to make your predictions more precise. One thing that I'll just mention here is that logistic regression is not fit by least squares. Okay. And so it's fit by something called the maximum likelihood estimation. We're not going to talk about it. It involves finding the derivative to find the maximum, right, and that kind of thing. But it is worth mentioning that logistic regression is not fit by least squares. But by maximum likelihood estimation. MLE. which is how I used to spell my name if I wanted to be cool when I was little. Um, so that's just something to kind of keep in mind. We're not going to talk about the maximum likelihood estimation. That's fine. But that is how it's fit. Okay, so logistic regression, right? We're talking about classifying as case 1 or case 0. So finding residuals or any other methods that rely on the residuals isn't really going to be that useful. So logistic regression, we're not going to have things like the RMSE or R squared. And so we need other methods for evaluating the model. Let's write that down. Logistic regression does not have an RMSE or R squared or anything like that. So we need other methods for evaluating the model. And that's what we're going to focus on today, is evaluating classification models. The first way that we can evaluate a classification model is just the accuracy. Okay, so the accuracy is an option, which is the overall proportion of correctly predicted cases. Overall proportion of correctly predicted cases. I will say that this is not very useful, right? Especially if we're trying to talk about how many ones did I correctly predict, right? So this is the overall proportion, which includes the number of zeros, right? So this is not very useful as a way of evaluating these classification models, right? Because we want to talk about, usually we want to focus on how many ones did I correctly predict. Okay, and usually there aren't as many ones as there are zeros. Let me just check to see I'm not missing anything here. Okay, good. So what we usually do is we build a confusion matrix, because either an observation is either a 0 or a 1, right, which we have in our data so we can check it, but I can also predict whether it's going to be a 0 or 1 using different cutoffs. So we can build a confusion matrix to split our correctly classified cases from our misclassified cases. From our misclassified cases. So the confusion matrix is going to look something like this, right? I have my predicted classification, and maybe I'll use a different color here. Predicted classification. Oops, weird. My screen did something weird. There is either 1 or 0. I've got my true classification, which if it's in my data, then I can just check it, classification, which is usually what we do when we're building models, right? The true classification is either 1 or 0. then if I predicted that something's going to be a 1 and it is a 1, that's a true positive. Which we'll abbreviate TP, true positive. If I predicted it was going to be a 0, but it's actually a 1, that's a false negative. Which we'll abbreviate FN. If I predicted it was going to be a 1, but it's actually a 0, that's a false positive. And if I predicted it was going to be a 0 and it is a 0, then that's a true negative. TN. Remembering that the predicted classification of 1 or 0 depends on the cutoff value, right? And so our confusion matrix would change depending on the cutoff value. So here, our predictions depend on the cutoff value. So the confusion matrix changes with different cutoff values. So the confusion matrix changes with different cutoff values, which is also a way that you could consider different cutoff values, right, is looking at this confusion matrix. So what we can do here is we can talk about the totals. Now the true classification, if it is 1, how we denote that is we use y equals 1. Or if it's 0, y equals 0. Remembering that the predicted classification, we use y hat, right? And so what we can do, just so we have some notation here, the predicted is either 1 or 0, and the truth is either 1 or 0. And we said that, okay, this was a true positive, this was a false negative, this was a false positive, and this was a true negative. Then, in order to establish some of these evaluation tools, we're going to need the totals as well. We're going to need shorthand for the totals. Y equals 1, y equals 0. The total for the predictions, y hat equals 1, y hat equals 0. I don't know. I don't think it would just be n, your overall total, but we don't need it. Okay, so we talked about one measure that we could use to evaluate classification models is accuracy. Now, we said that's not very useful. That's just overall how many were correctly predicted, right? So that's going to be what? The true positives and the true negatives, right? Those would be correctly predicted over n. There's something called sensitivity, which is another measure. It's also called recall. But usually when I write recall, it kind of makes me think of recall this, but that's not what I mean. The sensitivity or the recall is the true positives over the true ones, right? So what proportion of true positives, so correctly predicted positives out of the total ones? So recall is the proportion of ones that were correctly classified of all the ones that were correctly classified of all the ones. So if your focus is on the ones, then sensitivity is a good measure of evaluating the model. Another option, it looks like it's typed, but there's actually a page break here. So specificity in terms of that shorthand that we used is the true negatives over all the zeros, right? So the correctly predicted negatives over all of the zeros. So in words, the specificity is essentially the opposite of the sensitivity, is the proportion of zeros that were correctly classified of all the zeros. All the zeros. Another measure is precision. Precision is the true positives over all the predicted ones, right? Notice this is the predicted ones. So what does that mean? It's the true positives out of all the ones that we predicted to be ones. So the precision would be low, right? If I predicted a lot of them to be ones, right? But only some of them were truly ones, right? If I make my threshold 0.2 or my cutoff 0.2, I'm going to predict a lot of ones, and a lot of those will be true, right? I will capture a lot of those true ones, but I'm also going to have a ton of false positives. So that's where the precision comes from. So precision in words is the proportion of correctly classified ones of all the predicted ones. Of all predicted ones. So like we said, all of these, right, these true positives, false negatives, all of these depend on the cutoff value, right? And so we need some way to be able to decide what our cutoff value should be. Okay, and so one of the tools that we have is using an ROC curve. So to help decide on a cutoff, we can visualize the trade-off between the recall or the sensitivity and the specificity, right? Remember, these were kind of in cahoots, opposites of each other. And so what we do, decide on a cutoff, we can visualize the trade-off between the recall and the specificity. Using an ROC curve. Which stands for receiver operating receiver operating curve, or characteristic, sorry. Curve. So what we have, we're going to have the recall on one side on the y-axis and the specificity on the other. And along the diagonal, okay, so y equals x, right? That's the random chance classifier. Okay, what this means is if I just have a bunch of records and I'm trying to classify them as zeros or ones, I'm just going to randomly assign 0 and 1, and this is how well it would perform. So what we do is our model might give us something that looks like this. So this is the ROC curve. And what we want is we want to pick a cutoff where the ROC curve is as far away from the random chance classifier as possible. The random chance classifier as possible. Okay. So this is the curve, right? And we want to find some cutoff that kind of bumps this out. So what we're going to be talking about is the area under the curve. So the area underneath the curve, the AUC, is a metric that we can use to evaluate the model. The area, and I guess I should capitalize it, underneath the curve, AUC, is a metric we can use to evaluate the model. Evaluate the model. Just as a guideline, an AUC of 0.5, right? So the area under the curve is 0.5. This is an ineffective cutoff, whereas an AUC of 1 means that you have perfect classification, which is unlikely that you'll actually have that, right? But closer to 1 is good, right? So you want your AUC close to 1. Yeah. So a lot of the time, we're going to want to model rare cases, right? So like I mentioned before, we've got a ton of zeros and not very many ones, but the ones are what we're interested in, right? For example, who died from a vaccine, right? It's very rare, but that's what we're interested in modeling in, right? We don't really care about all the zeros, right? We're more interested in the ones. And so a lot of the time, we want to model rare cases, which is another way of saying that our sample has many, many zeros and very few ones. Our sample has many zeros and very few ones. This is what we call imbalance data. We call this, oops, imbalanced data. So just some of the options that we have for dealing with imbalanced data, it kind of depends on what the situation is. And sometimes it's good to play around with a few of these, but to deal with this, to deal with imbalanced data, we have a few options. One would be undersampling the zeros. So just to describe here, sample roughly as many zeros as there are ones. Sample roughly as many zeros as there are ones. Okay. One problem here is that this is going to ignore many zeros. And what we're talking about here is in terms of building your model, right? If we're undersampling, then your model is built on roughly the same number of zeros as it is ones, right? So that kind of makes the ones shine. But then we're also, right, one of the problems is that this ignores many zeros. So that's not great. But if you're okay with that, then that's okay. Another option is oversampling. Or we could call it up-down weighting, depending on which way you want to think about it. That's going to be when we resample ones to increase the number of ones, right? And so you're just resampling ones and just replicating them, right? Just like the bootstrap. But that's when we resample ones to increase the number of ones. Or you could, so the up or down weighting, you could apply a larger weight to the ones than zeros. So you don't have to physically reproduce them. You could just apply a larger weight. Or apply a larger weight to ones than zeros. One semi problem with this is that you're recreating ones we already have. It's not truly a problem, but you don't have really any new data, right? You're just amplifying the data or applying a weight to the ones. Now, the third option is called SMOTE, which stands for synthetic minority oversampling technique. SMOTE does, it is oversampling, but in a way where we're not just recreating ones we already have, we generate quote unquote new values of ones using predictors from existing ones. right? And so this was a 1 and some of the predictors, and so you do kind of a mashup of the predictors to kind of create ones that you don't already have is basically the idea of SMOTE. So it generates new values of 1s using predictors from existing ones. So that's kind of cool. And so here, right, what's nice about it, I guess I shouldn't write it in red, is that this does a combination of, so it kind of creates observations that we don't already have. Observations we don't already have. Right? But it uses the other predictors, right? And maybe a mashup of the other predictors. Okay. Good. My last note, I can't believe I only have one more little note about this section, because obviously we'll need to play around with this, which we'll do in the lab tomorrow. But beyond just classifying, so just purely classifying based off of the probability of being 1, right? There's often some sort of expected return for each classification. So you'll also want to consider that. So I'll just write that here, and then I'm pretty sure we'll look at an example in the lab, or I'll try to dig one up. So beyond classifying a record purely based on the probability of being class 1, right? Which is what the model yields. Which is what the model yields. All right, gives us the probability of being in class 1. We should also consider the expected return. The expected return, oops, for each classification. Usually that has to do with stock prices and things like that. So see if I can dig up an example for the lab tomorrow. And that's all I have notes on. I thought it was going to take a lot longer, but that's okay. I'll come back here. Whee. If you guys have any questions, let me know. Otherwise, I'll post the lab and you can work on it on your own time. But I'll be there, but only for the first 15 minutes. If no one's there after 15 minutes, I'll take off. But otherwise, have a great weekend. I'll stop this recording.